Once again, our modelling, nothing changes once we're modelling. A lot of the key terms mean the same thing all the way through. In this case, I happen to be given a rate of change. We're saying that our ant farm population is changing at a rate, dNdt equal to. Okay, so it's a positive exponential, so it's increasing. All right, so if I want to find the relationship for n, it means I need to anti-differentiate both sides with respect to t, which is what we've done there. Integral of 20 e to the 0.2t dt. Anti-differentiate. Okay, so what do? We 1 on k, e to the kx. So 1 on 0.2, e to the 0.2. 20 over 0.2, well, 0.2 is 1/5. 20 on 1/5 is 100. So you might need to just be a little bit careful if it was a tech-free environment of getting your fractions. So there's my antiderivative plus some constant c. Initial condition, we were told at t equal to 0, the population was 50. Yeah. Initially there were 50 ants. So if we substitute those values in, e to the 0 is 1, I get c equal to negative 50. So there's my general rule for the population of ants at any point in time. Okay, so there's a function in terms of t, in terminology. And then finally, after 8 days at t equal to 8, n is 100 e to the 0.2 times 8 minus 50, which if I go to a CAS printout, I should have put an answer down, equals 445, doesn't really say. I guess you could argue, you could leave it an exact value, so 445 ants. All right. If we're going to make use of our CAS, obviously we've got the antiderivative here. So I know you can't quite see the top line, but notice if I put 1/5 in as the 0.2, okay, an exact value, we get the answer in the format we're expecting. You can just sort of see there I've got 0.2 just at the top of the screen there, which gives me a decimal equivalent. Okay, so I think it's probably better off when we integrate, try to use exact values whenever possible. All right, it's not always possible, but if it is, use the exact values. So there's my antiderivative. So I know that that antiderivative plus some constant c, you know, if it was a bit messy, you can put in your initial condition there to get your c value. And then at t equal to 8, that function is equal to 445.3. All right. The linear motion is an area that we've looked at with our differentiation and the differentiation of our functions. So what we're talking about is our displacement, velocity, and acceleration. And what we know is that the displacement or the position, if we differentiate it, that gives me my velocity. So velocity is the rate at which my position changes over time, dx dt, and acceleration is the rate that my velocity changes over time. Yeah. So that means that if I integrate the acceleration, it takes me to my velocity. And if I integrate my velocity, it takes me to my displacement. All right. So it's really important to keep those processes clear in your mind. A couple of other terms that we've spoken about before: average velocity, change in position over the change in time. Instantaneous velocity, well, that's my derivative, dx dt. So average anything, y2 minus y1 over x2 minus x1. Instantaneous anything, it's the value of that rate at a point. So it's going to be a derivative. So if we have a bit of a look at this example, we've got a particle given by x of t equals, displacement is measured in meters, time in seconds. Find the initial position, which is t equal to 0. Yeah, the position after 2 seconds, put t equal to 2, it's still at 0. So I guess in terms of terminology here, my displacement is 0. Yeah, so looking at the graph, at t equal to 0 to t equal to 2, I'm back to where I started. So my displacement is 0. The distance traveled, well, that's a little bit different. You know, I've moved, as it turns out, well, let's get to it. Instantaneous velocity, dx dt, so the derivative of x is 2t minus 2. So when and where the particle is at rest? Well, we're at rest when the velocity is 0. So if I solve my velocity equation equal to 0, I get t is equal to 1. And at t equal to 1, if I put it into my position, I'm at -1. And -1 simply means we're, I guess, 1 meter to the left of our starting point. Yeah. So typically we sort of, is it to the left or to the right? Probably to the right, actually. So positive, well, in a negative direction. It may not be left or right, to be honest. So we're 1 meter behind our starting point. Yeah. When we stop. Acceleration of the particle, dv dt, which gives me 2. So our acceleration is 2 meters per second all the way along. So in terms of the motion of my particle, if that's my starting point there, what's happened is I've gone in a negative direction for 1 meter, and then I've stopped and then traveled in a positive direction. Yeah. So that 1 meter took, as it turned out, 1 second. So I traveled in a negative direction for 1 second, and then I turned around, and then after 1 second heading in the other direction, I'm back to where I started. So after 2 seconds, I'm back to where I started, but in fact, I've traveled 2 meters. So displacement equals 0, but distance traveled equals 2 meters. So that's really important. And then I continue to travel in a positive direction for the rest of the journey. All right, off you go.